Hello, and welcome to our video describing the ins and outs of experimental atomics' photoelectric effect lab. Following the ultraviolet catastrophe of the late 19th century, Max Planck first postulated that light was made of discrete energy packets that seemed to hold the properties of both particles and waves. Flying in the face of the laws governing classical mechanics, Planck's assertions were met with skepticism, to say the least. It wasn't until Albert Einstein's Nobel Prize-winning work in 1921 that all doubt was set aside. Here, you'll be looking to replicate and reinforce Einstein's findings regarding the interaction of light and matter. Still, we may be getting ahead of ourselves. Let's start with some theory. For the purposes of this lab, we can view photons as small packets of energy. The energy of each packet is proportional to its frequency, nu, based on the equation E equals h nu, with h being the Planck constant. When light strikes the surface of a material, these packets are absorbed by the atoms within. This absorption, in turn, excites the atom's electrons into higher energy states. When given large enough energy, this absorption can cause electrons to be emitted from the material as free particles. Albert Einstein coined this weird phenomenon the photoelectric effect, and further asserted that the kinetic energy of the emitted electrons was equivalent to the energy of the individual photons, h nu, minus a second term coined the work function, here noted as phi. The work function can be thought of as the smallest amount of energy needed to free an electron from a surface. Therefore, the magnitude of the work function is material dependent. So how do you quantify the kinetic energy of the emitted electrons? For this lab, our apparatus will essentially consist of two plates, an anode and a cathode. Classical mechanics predicted that the kinetic energy of the electrons emitted would be proportional to the intensity and wavelength of the light source. Oddly enough, this was found to be incorrect. In 1900, Philip Leonard showed that the kinetic energy of the electrons was solely based on the wavelength of light, and not the number of photons. A voltage will be applied to both plates in order to create a potential within the chamber. Our light source will strike the cathode to produce an electron that then enters into this potential between the plates. Instead of trying to gauge the speed of the emitted electron directly, we'll be doing the opposite. We'll be finding the amount of energy needed to get the electrons to stop moving. Remember, electrons carry a negative charge. Inside of our potential, the electron will be slowed based on its charge E and the magnitude of the voltage applied to the plates V. When the kinetic energy of the electron and this quote-unquote stopping potential match, the electron will be unable to move and current between the plates will stop. Luckily, our apparatus determines the voltage where this occurs automatically, so all we need to do is attach a voltmeter to our apparatus and wait. Speaking of our apparatus, let's get into the procedure. We'll be using a few different pieces of equipment. The biggest box on the table is the mercury lamp. Connected to the lamp via a hinge is the apparatus talked about earlier that produces the potential. Connected via banana clips is our voltmeter. Note the wiring. No clips should go into the battery terminals. Make sure the meter is set to DC voltage and a sensible scale. 2 volts should be fine. Our diffraction grating and its holder should be on the table along with a few filters. These should be a green filter, a yellow filter, and a transmission filter. Start by turning on the mercury lamp. These lamps can take a while to warm up, so it's best to turn them on while preparing the rest of the pieces. Attach the diffraction grating holder to the lamp by sliding it into the vertical grooves. The diffraction grating can then be placed on the 2 rods, but don't fasten the screws yet. Next, turn on the switch on the side of the apparatus. For a quick check to make sure all the necessary spectral lines can be seen, take a blank piece of paper and hold it in front of the grating. Make sure both the first and second order lines are visible. If all the lines are there, now we can focus. Move the diffraction grating forwards and backwards along the rods to the position where the spectral lines are sharpest. Once you're confident that you've gotten the lines as sharp as you can, tighten the screws on the diffraction grating to avoid shifting the focus. Throughout this experiment, you'll need to align the spectral line you're interested in with the slit of the apparatus before collecting any data. Remember, simply having the line hit the slit does not mean the line is hitting the detector. Once you think you have the line hitting the slit, open the shield of the apparatus and make sure that the spectral line is hitting the detector. The shield is there to make sure that outside sources of light other than your lamp don't skew your data. Still, minimizing exterior light goes a long way towards reducing error for this lab. Now we're all set for Part A, the relationship between stopping potential and intensity. Start by aligning the blue spectral line with the detector of the apparatus. For the first part of the lab, we'll be seeing how long it takes for the stopping potential to stabilize. Take out your phone or any other stopwatch you may have. Have your partner discharge the apparatus using the discharge button on the side and start timing. You should stop your timing once the voltmeter reaches a stable voltage. It doesn't have to be too precise, but just get a good general idea. Now, let's see if our setup seems to give us what we'd expect for stopping voltage. Document the stopping voltage when the blue line is aligned with the detector. Next, switch to the violet line and document this new stopping potential. We can check that our data is close to what we'd expect theoretically by taking the difference between the two stopping potentials. Using what we know about the energy of photons, we can set up an equation based on the two wavelengths, lambda1 and lambda2, the Planck constant, the speed of light, and the stopping potential difference. With some easy algebra, we can solve for h times c, which is a constant, and should be around 1240 eV times nanometers. Figure 5.3 includes a table of wavelengths for each line that should help with this section. If your calculated value seems reasonable for what you'd expect for h times c, we can get started on our intensity measurements. Align the blue spectral line once more. Place the transmission filter over the slit of the apparatus. Take note of the sections of the filter. Each one corresponds to a specific percent transmission for incident photons. Starting with 100%, document the time until the voltage stabilizes and the magnitude of the stopping potential at that point. Do this for each of the 5 sections of the filter. Make sure to discharge the apparatus so that no charge stays within the plates between runs. See if you notice any pattern in your data. For Part B, remove the transmission filter. If all went well, we should be done with our intensity data. For this section, we'll be documenting the stopping potential corresponding to each specific spectral line. One line at a time, align and discharge the apparatus. Make a note of each of the stopping potentials once the voltage stabilizes. Before we get too far into our data collection though, let's take a second to address our first order yellow and green spectral lines. Record values for the stopping potential for the yellow and green first order lines with and without their respective green and yellow filters over the slit of the apparatus. Do you notice anything peculiar? Talk to your TA or professor and hypothesize what might be going on and how you can adjust for this in your data collection. After that, collect data for the stopping potential of each line. There should be 5 colors with first and second orders for a total of 10 data points. That concludes our data collection, which means we can do some analysis. Before doing anything with your data, take a second with your lab partner and discuss the uncertainties for your measurements. Did stray light have any effect? What about alignment of the lines? Make sure to account for these issues in your data analysis. Take a look at the data taken with the transmission filter. What effect did varying the percent transmission have on the stopping potential? What does this mean about our photoelectrons? Was there any difference in your charging time for the apparatus? Take a look at the appendix of your manual and think about why there is a slight drop in the measured stopping potential as the light intensity is reduced. When we change the wavelength of light, what happened to the stopping potential? What do these two findings tell us about light and the photoelectric effect? Is this effect classical or quantum? Why or why not? Next, let's graph our data from Part B. Make a plot of stopping potential versus light frequency for the first and second order data. Remember, the frequency values for the spectral lines are given in figure 5.3. Theoretically, these two graphs should be linear with a slope equal to the Planck constant. The absolute value of the y-intercept should be equal to the magnitude of the work function. Based on the calculated work function here, make an educated guess about what type of material the detector is made of. Is it a simple metal like aluminum or copper, or is it something else? How is the fit of your plot? Does it match exactly? That concludes Experimental Atomics Lab on the photoelectric effect. Thank you for watching.